Good afternoon, those who are with us at this defense. And this defense also is being presented in line with the 1UP Applied Mathematics weekly webinar series. So we welcome those who are also tuned in for that. This afternoon, we will be listening to Ms. Angeli Ferolino in defense of her master's thesis entitled Optimal Location of Sensors for Early Detection of Tsunami Waves, which she did research for which was done under the supervision of Dr. Jose Ernie Lope and Dr. Renier G. Mendoza. So, Ange, you have up to 45 minutes to deliver your presentation. After this, we may entertain questions from the audience and panel members, and then we will have to do close deliberations among panel members. I hope this format is understood.
Yes,
And okay, we will now request Angeli to start.
So, good afternoon. I am Angeli Ferolino, and I'm here to discuss my thesis entitled Optimal Location of Sensors for Early Detection of Tsunami Waves. This is my research, along with my advisors, Dr. Lope and Dr. Mendoza. So this will be the outline of my presentation. First, I will introduce my topic and the motivation behind it. Then I will discuss the optimization problem, the methods used to compute the wave travel time, and the population-based algorithms used to solve the optimization problem. Then I will show the numerical results. Lastly, I will discuss the conclusion and some recommendations for future works. So tsunamis are a series of sea waves which are commonly generated by undersea earthquakes. Unlike normal sea waves, their wavelength is much longer, so when the depth of water decreases, they build up to higher heights. Moreover, they can travel at around 500 miles per hour. In the Philippines alone, a total of 41 tsunamis occurred since 1589. Tsunamis are considered as one of the most destructive natural disasters, and with a large volume of water moving at a high speed, they can cause massive destruction to the physical environment and can cause loss of human lives. So, it is important for us to assess the risk and mitigate the impacts of the tsunami. So, in this research, our goal is to provide early tsunami warnings so that people can have time to prepare and evacuate if needed. One way of doing so is by determining the optimal location of tsunami sensors that can minimize the tsunami detection time. So we have the optimization problem as this. First, we let omega be a domain with parts of water, D be a part of the domain where the tsunami sensors can be placed, and P be the subduction zone. Our problem is to find the location of L sensors such that any seismic event on P will be detected after minimal possible time. As a notation, we let big Q be the set of L sensors. Now, suppose that some disturbance arises on a source PJ in P. This disturbance will propagate over water at a certain speed. Now, we let X be some water point in D. So what we are interested in is finding the minimal time it takes for the disturbance from source PJ to reach X. So we let gamma be one of the ways connecting PJ and X, and tau of gamma be its travel time. We denote tau PJ of X be the minimal time it takes to approach X from PJ, and it is given by this equation here. Now, since we may be dealing with multiple sensors, the time required for determination of a tsunami wave by Q is calculated as this equation, wherein we take the minimum of tau over all sensors. So we do this because the determination of a tsunami is does not require determination by all sensors. One is already enough. And since we want early tsunami warnings, we take the minimum. Now, for guaranteed time registration for any point Pj in T by Q, we have this, we calculate this equation wherein we take the maximum of small t over all the source points. So basically, we do this to accommodate all the source points wherever they may be. Thus, we have the statement of the optimization problem formulated as the following. We want to find the set Q, which will bring the minimal value to the function big T of Q, where the number of L is given, and we have phase restrictions. That is, Q must be in D. Recall from earlier that D here is the part of the domain where the tsunami sensors can be placed. Now, one of the key points in solving the optimization problem is determining how we can compute for tau here. So in my thesis, we use two methods. By the way, this is an sample illustration of a domain. So we have a rectangular domain. D is the water area, and P is the semicircle subduction zone. So anyways, we for computing the wave travel time, we use two methods, starting with illustrating the kinematics of a wavefront. So for this method, we will consider the linear approximation of the shallow water equations. And in this case, we have this as the approximation of the wave velocity. G here is the gravitational acceleration equal to 9.81 meter per second squared, and H is the water depth. Note that for any propagation velocity distribution in a medium, all the points in a wavefront are moving towards the orthogonal direction. And this will be our basis for the step-by-step wavefrontal line advancement. So for the first step, we first consider a closed and convex curve, for example, a circle, as the initial wavefront. This wavefront will be presented by a limited number of computational points along the curve. As an illustration, here is an initial wavefront with computational points along the circle. Now, our goal is to determine the next position of these points. So, to determine the next position of a point, say xi, yi, we will compute its moving direction, and it is determined by the outer normal of the circle passing through these 3 points here, or the neighbor points of xiyi and xiyi. Then, we will move the point xiyi in this direction with a distance of v times delta t, where delta t is the time step. Doing this step to all the computational points, we will obtain the wave propagation of the initial wavefront at the time instant t equals delta t. Then we will repeat the entire process until we reach the boundaries of the domain. So here is an illustration of how the initial wavefront from the earlier slide will propagate over water with constant depth after 15 seconds. Now note here that we know the travel time to all the computational points. So to determine the travel time to any point in the domain, which is not necessarily a computational point, we will use linear interpolation. Now recall from the first method that we only use an approximation of the wave velocity. So for us to obtain more accurate solutions of more accurate solutions of the wave travel time, we will solve the 2D nonlinear shallow water equations. So the shallow water equations are a set of hyperbolic partial differential equations that describe fluid flows. They are often used to describe geophysical flows such as in rivers, lakes, coastal areas, etc., rainfall runoff, tsunami propagation, and even atmospheric flows given the appropriate initial conditions and source terms. Some assumptions in the shallow water equations are the following. The horizontal length scale is much greater than the vertical length scale, meaning the wavelength is much greater than the depth. We also have very small vertical velocities, and so the vertical pressure gradients are nearly hydrostatic. And we are working with incompressible fluids, meaning the density is constant. So here is the 2D nonlinear shallow water equations. We have here H as the local water depth. U and V are the velocities in the x and y directions respectively. G is the gravitational acceleration, and the gradient of C is the bed slope. An equivalent form of this shallow water equations is this, which is derived by letting H is equal to eta minus Z with eta as the surface elevation. Note that we can write U sub x, B U sub y, UB sub x, and VB sub y, the terms here, in terms of U sub q equals HU, V sub q equals HV, U, V, and H in using relations 4 and 5. Now, to solve the 2D nonlinear shallow water equations, we will use the finite volume method. So the finite volume method is a numerical method for solving partial differential equations that calculates the values of the conservative variables across the volume. So as an illustration, if the conservative variables are defined at the black points, then the corresponding orange square is its corresponding volume. To discretize a certain partial differential equation using FBM, here are its steps. First, we divide the domain into parts, and these parts will be referred to as the control volumes. So this is what we have shown in this illustration here. Then we will integrate the equation over that volume. We will use Gauss theorem to transform the volume integral into a surface integral. And upon evaluating that integral, we will obtain the discretization of a certain PDE using finite volume method. Now, for solving the shallow water equations, I use a staggered grid for the finite volume method. In a staggered grid, this is its illustration. The H is defined at the cell, at the center of the cell. Then U and V are defined at the center of the cell faces. So the control volume for H is this square, U is the green square, and V is the purple square. By implementing the 2D staggered grid finite volume scheme on the shallow water equations, we obtained this approximation for the mass equation at the cell centered at Xij, where we have this upwind approximations. So we do this because H is not defined on the half-step points. And we also use upwind approximations for us to determine the direction of flow. For example, if the flow is positive, Hi plus 1/2 j is equal to Hij. Then if the flow is negative, it is equal to Hi plus 1j. The approximation of the momentum equation in the x direction is implemented at the cell centered at xi plus 1 half j, and the momentum equation in the y direction, or the equation 3, is implemented at the cell centered at xij plus 1 half. We will also use the relations 4 and 5 from earlier for the approximation of the advection terms ux, uvx, vu sub x, vu sub y, and vv sub y. So if we have positive flow directions, we have this as the discretization. We have this as the approximation of the momentum equations, where we have the following. So similar to the mass equation, we use upwind approximations for the fluxes, while for the other terms, we take the average. In solving the shallow water equations, I use an explicit scheme, and because of that, we need to carefully select the time step to maintain numerical stability of the equation. So Curran, Friedrich, and Lully defined as stability conditions for fully explicit schemes given by this inequality here, where C is as such. So by this equation, we can calculate delta T, and we can take C equals 0.5 to obtain the time step use for the numerical scheme. So here is an example simulation of the 2D shallow water equations. We define our domain to be in the interval -5 to 5 squared, and we have this initial conditions. The velocities are equal to 0 and h is equal to such. So this signifies a single hump of water. We also have 0 velocities at the boundary conditions. Also, we assume a flat bottom topography. So d of xy is equal to some constant value. So if we have this single hump of water, this is how it will propagate over water with a constant depth. Now, we discuss the population-based algorithms that we will use to solve the optimization problem. Starting with the genetic algorithm with multi-parent crossover. So the genetic algorithm is an evolutionary algorithm based on a natural selection process. So this algorithm mimics biological evolution. In the algorithm, it first initializes by having a random population. Then, to produce the next generation, the algorithm will select individuals to use them as parents. And we have 3 types of children. First is the elite. So these are individuals in the current generation with best fitness values or objective function values. The mutation children are created by making some random changes in a single parent. And the crossover children are created by combining vectors from a pair of parents. So this is the flowchart of the genetic algorithm. However, GA is known to be slow, and sometimes it cannot converge to the global optimum. So we considered a modified genetic algorithm called the genetic algorithm with multi-parent crossover. And here, the crossover and mutation processes were modified. For the crossover process, instead of using 2 parents, we will use 3 parents, and they will generate 3 offsprings. 2 of those offsprings are to help exploitation or improving the current solution, while the other one is to promote exploration. After a crossover, the algorithm will implement a randomized operator with some probability on the generated offsprings to further diversify them. So this is important because it helps the algorithm to help escape local optimum solutions. Here is the flowchart for the GA-MPC. After initialization, we select the best M individuals and store them in the archive pool. Then we will apply a tournament selection of some size to fill the selection pool. So in this pool, this is where the parents are selected. And these parents are used in the crossover process. They will generate 3 offsprings, as in this box here. Then after crossover, we will apply mutation. And then we will do this entire process until we reach the stopping criteria of the domain, stopping criteria of the algorithm. Next is the particle swarm optimization algorithm. So this is a population-based algorithm which characterizes a collection of individuals known as particles as they move in steps throughout the region to find the global minimum. The trajectory of each particle in the search space is adjusted iteratively by updating their velocities, which takes into account their own experience and the neighbor's experience. So it is done this way to help balance exploration and exploitation. This is the flowchart of the PSO. After initialization, we will evaluate the cost function for all particles, and we will determine the G-best and P-best values. So G-best stands for the best location of the swarm, while P-best is the best location attained by each particle. Then we will use the G-best and P-best values to update the position and the velocity of the particles. Again, we will do this entire process until we satisfy the stopping criteria of the algorithm. For the last algorithm, we have the rainfall optimization algorithm. And this is a new nature-inspired algorithm based on raindrop flow over a mountainous surface. And here is an illustration of the model. Note here that when it rains, the tendency of each raindrop is to fall on surfaces with a steeper slope, and they will fall downwards until they reach an optimal solution. And this can be a local optimal solution. However, as raindrop accumulates, the water will soon overflow, and again, it will fall downwards until eventually it will reach the global solution. Before discussing the algorithm, we first define some relevant terms. First is the raindrop. This is the particle in the population denoted by this, where M is the population size, N is the number of optimization variables, and Xij is the variable of interest. Note that the generation of raindrops are uniformly randomly distributed and must be within the bounds if there is any. Next is the neighbor points. So these are points within a neighborhood of radius r of a raindrop. This is denoted by NP I sub k and must satisfy this inequality. Here, Uj is the unit vector in the jth dimension, and NP is the number of neighbor points. Our goal in this algorithm is to determine a dominant neighbor point. So a dominant neighbor point is a neighbor point whose cost function value is less than the cost function values of the raindrop and the other neighbor points. If a raindrop has a dominant neighbor point, then it is active. Otherwise, it is inactive. If a raindrop has no dominant neighbor point, then it means that it has either converged to the global solution or it is stuck in a local solution due to insufficient number of neighbor points. So for us to prevent the latter, we apply an explosion process. So this is a process that produces a new set of neighbor points of this number here in this equation, with EB as the explosion base and EC as the explosion counter. So note here that when we continue applying the explosion process, the number of neighbor points increases iteratively. As a remark, if the drop still has no dominant neighbor point, after doing the explosion process any times, then we will make it inactive. We do it like that because it means that the raindrop has already reached the global optimum. For the last term, we have a merit order list, and this is a list containing the rank of the raindrops in ascending order. Here, the lower ranking raindrops may be removed from the population, or higher ranking raindrops may be given special rights, such as higher number of explosion process. We have this as the calculation of rank, where F is the objective function. So basically, a raindrop is of low rank if it has a small cost function value, or it has exhibited large improvement regarding its cost function value, while the opposite can be said for higher ranking raindrops. And so, lower ranking raindrops are near the global solution, while higher ranking raindrops are still far, so they still need to be more active in searching. So here is the flowchart for the RFO algorithm. After initialization, we will set each drop status to active. Then we set the drop number to be equal to 1. If the first raindrop is inactive, then we will proceed to the next raindrop. Otherwise, we will generate neighbor points and calculate their cost function values. If there is a dominant neighbor point, then we will update the position of the raindrop to the position of the dominant neighbor point. If it has no dominant neighbor point, then we will apply explosion process. If a dominant neighbor point is found, then we will update the position of the raindrop. Otherwise, we make it inactive and then proceed to the next raindrop. We will do this entire process to all raindrops. And after that, we will create a merit order list. And here we will set the lowest ranking raindrop to inactive. Again, we will do this entire process until we satisfy the stopping criteria of the algorithm. So here are my numerical results. First is we consider the problem of determining the optimal location of sensors in a rectangular domain with a semicircle subduction zone, as we can see in this figure. Here we assume that we have a flat bottom topography, meaning meaning we have a constant water depth. So here is the optimal location of one sensor. Note that it is located at the center, and this makes sense since if we have a constant water depth, then the wave travel time depends on the distance. And here, all the source points in the semicircle are equidistant to the center. That's why we have the center as the optimal location. Here is the optimal location of 2 sensors, 3 sensors, then 4 sensors. And we note here that when the number of sensors increases, they mimic the shape of the subduction zone. Also note here that the black, yellow, and green points are the optimal location attained using GA-MPC, PSO, and RFO respectively. Moreover, the numerical results presented here in this slide and in the previous slide are attained using the first method. Now for the second method, this is the optimal location of one sensor, two sensor, three sensor, and four sensors. And from here, we can see that in both method 1 and method 2 exhibit similar results. Now here is the table showing the tsunami detection time for some number of sensor using both methods and the three algorithms. We present here the average and best values as well as the standard deviation. By the way, I did 10 independent runs for each method and each algorithm. So here are the tsunami detection time values for one sensor and two sensors. And here is for the three sensors and four sensors. And we can see from here that we have very small standard deviation, and the average and best values are close to each other. Also, we can see from here that we obtained the best tsunami detection time using method 2 and PSO. And so we will use PSO and method 2 for the rest of the results. Now here we examine how the number of sensors can affect tsunami detection time. And as we can see from this figure, as the number of sensors increases, the tsunami detection time decreases. Moreover, note that when we increase the number of sensors from 4 to 5, there is only little improvement in the tsunami detection time. And so we can say that 4 is a good number of sensors that will give us good tsunami detection time without introducing extra cost of having an additional sensor. Here is the table of values showing the tsunami detection time and how much is the decrease in time from n-1 to n sensors, where n is the number of sensors. Now, we examine how a different bathymetry will affect the optimal location of the sensors. We consider an inverse tangent bottom topography as shown in this figure. So from here in the left side, or the area with lower values of x, we have a larger depth, while on the right side, we have a shallower area. So this is the optimal location. So this is the optimal location obtained for one sensor. The black is the optimal location obtained using if we have a flat bottom, and the pink one is if we have the inverse tangent bottom. And we can see here that the optimal location moves towards the right. And this phenomenon happens because waves travel slower in shallower areas. We also did the same for the if we have two sensors. So if we look at the right sensor, the sensor moves upwards and rightwards, and this happens to accommodate the sensors on the shallower area. So with these sensors. Now in the this source points, I mean. Now for the left sensor, it moves downwards and slightly rightwards, and it is because it needs to accommodate the center source point. This center source point is located at the sloping part of the bottom. Now note that even though the sensor moves away from the source points here in the left side, it is okay because waves travel faster here because it has a larger depth. So these numerical results are obtained using PSO and method 2. Now, lastly, we consider the real-life problem of determining the optimal location of sensors in the Cotabato Trench. So this is the Cotabato Trench, and this is its bathymetry profile. Using PSO and method 1, this is the optimal location of one sensor, two sensors, 3, 4, 5, and 6 sensors. While if we use PSO and method 2, this is the optimal location of one sensor, two sensors, 3 sensors, 4, 5, and 6. So again, we examine how the number of sensors will affect the tsunami detection time. And we can see here that as the number of sensors increases, the tsunami detection time decreases. Also, uh, when we have 6 sensors to 7 sensors, there is only a little improvement in the tsunami detection time. And so 6 may be a good number of sensors that will give us good tsunami detection time without introducing an additional cost. Here are the table of values for the tsunami detection time and how much is the decrease in time from n-1 to n sensors, where n is the number of sensors. So in conclusion, we considered the problem of optimal placement of tsunami sensors that will minimize tsunami detection time. We use here 2 methods to compute the wave travel time and 3 algorithms to solve the optimization problem. From the results, we have shown that there is not much difference when we use either methods to compute the wave travel time. So if we want a faster computation of the optimization problem, one can rely on method 1. However, if we have complex geometries and bathymetries, it is better to use method 2 for more accurate results. Some recommendations for future works are these. First, one can investigate the optimal number of sensors that will not only minimize tsunami detection time, but also the cost of having additional sensors. Another recommendation is to consider maximizing the tsunami warning efficacy as an additional objective function. So here, the goal is to maximize the number of people that can be saved. And so to do that, one can put more weight on areas with a high population. So that's it. Thank you for listening. Here are my references.